I came here and set up the things. Okay. So in yesterday's class, in the previous class, we had discussed Hopkinson test. So this was the connection where we had seen the motor and generator are back-to-back connected, and first motor is excited to give the rated speed, then the generator is excited to give the rated voltage, and both are same, then the switch S is closed. When switch S is closed, we started uh, loading the MG set either by decreasing the excitation of the motor or increasing the excitation of the generator. So by doing this, we varied the load until the rated current, and once the rated current was obtained, we noted down the values of currents and voltages. Then we followed these calculations with which we got stray losses. From stray losses, we calculated the efficiency. Okay, with alternative connections, the fields were connected directly to the supply. Therefore, while calculating stray losses, we did not consider the field losses. Okay, but whereas field losses are the part of motor losses, hence we considered field losses when we calculated the motor losses, total motor losses or total generator losses. Okay, so this much we had seen. The advantage is that uh, with a very less amount of power drawn from the supply equal to only the losses, both the machines are operated at full load. Because machines are operated at full load, we can study the temperature rise and commutation effect. Okay, and also we can observe the variation in the iron losses because of the flux distortion due to armature reaction. Okay, the disadvantage is that the initial cost is high. If I want to test only one machine, then also we have to construct two machines. Okay, that will increase the cost for this type of testing. So next we'll move to example. Now, two shunt machines were tested using Hopkinson's test. Two shunt machines were tested using Hopkinson's test. Take line current of 2 line current of 15 amps at 200 volts. Of 15 amps at 200 volts. The motor 100 amps. The current is 100 amps. And the shunt currents are, and shunt field currents are 3 amperes and 2.5 amperes. If the armature resistance of each machine is armature resistance of each machine is 0.05 ohms, calculate efficiency of each machine. Calculate efficiency of each machine. for given load condition. Given load condition means with the currents whatever it is taking now. Okay, so those currents we have to consider. Yeah. This is a solved example in the textbook. Okay, but there is a small mistake done in this, so I have taken it directly. Okay, what it is done, I will tell you. Okay, there is a small error in the calculation. Yeah, the given things are. Now first we will draw the circuit diagram, because until I draw the circuit diagram and assign the currents, okay, in all the calculations we assign the currents that we have seen in the uh, calculations. Okay, but you should also be able to understand the KCL that is used there in assigning the currents. Okay, so here one more thing we should observe: should I follow the alternative connection or the first connection? That is one important. Should I follow the alternative connection or the first connection? Okay, so if alternative connection has to be followed, then it will be mentioned in the statement that fields are separately excited or fields are externally supplied. If these kind of statements come, fields are separately excited or fields are externally supplied or fields are directly connected to the supply system, then that is alternative connection. Okay, if nothing is mentioned about the type of field connection, then by default we should take the connection in which the fields are connected in shunt with the armatures, which gives the self excitation mode. Okay, so let us first draw the circuit diagram. Now switch and all we don't need, directly I will connect, because already the switch has been operated, the short circuit has been done between M and G, and the currents are obtained. Okay, and even and all also I will not use, we don't need that. Okay, so the given voltage is 200 volts. Now first assign the currents. We will follow the same current nomenclature as we have seen. So let this be I1. So let this be I2. Let the field current of motor be I3. Let the field current of generator be I4. Therefore, this will be let this be IAM. Let this be IAG. Okay. Now, it is clearly mentioned that the line current is 15 amperes. So therefore, my I1 is 15 amperes. Okay. They haven't mentioned anything about the generator line current. Whereas the motor current is 100 amperes. What is motor current? This is the motor current, I1 plus I2. The current that is supplying to armature as well as field. So motor current is equals to I1 plus I2 is equals to 100 amperes. I know I1 plus I2, I can get I2, not a problem. Then the shunt field currents are, see, it is not mentioned clearly which field current is for what machine. It is not mentioned in the statement whether 3 amperes is for motor or generator, 2.5 amperes is for generator or motor. So here we should understand the concept of Hopkinson test to assign the currents. We know that one machine is under excited or one machine is weakly excited, one machine is strongly excited. It means one machine's excitation or the field is weakened, which is operating as motor. Other machine's field is strengthened, which is operating as generator. So what will be the motor field current and what will be generator field current? Can you guess? Anybody? Okay, you are not interested. Fine. So here, when the field weakening happens, the field current decreases. So whenever this kind of field currents are mentioned without actually mentioning which field current is for, then by default, lower value of field current is for motor, higher value of field current is for generator. Okay. Here you take a note, because most of the times the field currents are mentioned like this only. Note, lower field current is for motor, higher field current is for generator. So in the textbook they have made this mistake. They have taken 2.5 amperes for generator and 3 amperes. So only I took example as it is. Yeah, so this is a small error. It has been done there in the textbook solution. Okay. Now, if it is exclusively mentioned that 2.5 ampere for generator, 3 ampere for motor, then we have to consider as it is. But if it is not mentioned, then by default, lower value will be for motor, higher value will be for generator. But generally, it will not be mentioned. Lower value for generator and higher value for motor. Okay. Then my I3 is 2.5 amperes and I4 is 3 amperes. Am I audible, right? I am connected.
Yes,
Yes,
sir.
sir.
So whenever I ask one or two small questions, you please reply, or else last in the one of the previous class for your higher SEM, half an hour there was no connection and nobody informed me back on phone. So I was continuously teaching. I solved the entire design example, and when I saw the recording for 25 minutes, the recording was stopped. Okay, none of the students informed me back that connection is lost, because we will be on the other screen. I can't see that Google Meet home screen. So there, if I will be there, then I will be knowing whether we are connected or not. Okay. So if I ask any small questions, some answers, you reply. I will be ensured that their connection is intact. So every time, whenever I get doubt, I have to change the screen and check. Okay. Fine. Now, RAM and RA equals to RAG. Both are same values. It is 0.05 ohms. The machines are identical. Okay, so this is the given things. Then what is solution? I2 is equals to the line current of motor, a generator. Generator line current is equals to, okay, I2 is equals to 100 minus I1. 85 amperes. 100 ampere is the motor current, I1 plus I2. I1 is 15 amperes. Okay. Then first we calculate stray losses. Stray losses, WST, total stray losses. Expression for total stray losses, I will directly be using the equations. Okay. So total stray losses is V into I1 minus all things. V into I1 is the input, line input, minus motor armature current square. IIM square RA plus V into I3. Now what is IIM here? Because there is no space, I have taken IIM and IAG. Okay. So here I will write IIM is equals to I1 plus I2 minus I3. So it is 100. I1 plus I2 is 100 minus I3 is 2.5, which is equals to 1.5 amperes. Okay. So, ಯಾವ್ದು ಇದಾ ಇಲ್ಲ ಇಲ್ಲಿಂದ ಇದಾಯ್ತಲ್ಲ 27 ಇಲ್ಲ ಇದು ವರ್ಕ್ ಫ್ರಮ್ ಹೋಮ್ ಇದು ಫುಲ್ ನನ್ನ ಫುಲ್ ಇದು ವರ್ಕ್ ಫ್ರಮ್ ಹೋಮ್ ಇಲ್ಲಿಂದ ಇಲ್ಲಿವರೆಗೆ ವರ್ಕ್ ಫ್ರಮ್ ಹೋಮ್ 27th ವರೆಗೆ ಫಸ್ಟ್ ವೀಕ್ ನಾನು ವರ್ಕ್ ಫ್ರಮ್ ಹೋಮ್ ಹೋದೆ ನೆಕ್ಸ್ಟ್ ಲಾಕ್ಡೌನ್ ಆಯ್ತು ರಜನಿಕಾಂತ್ ಸರ್ So square RA plus V into I3 plus IAG square RA G plus V into I4. Okay. So what is IAG? I2 is here somewhere I will write it down here on G is equals to I2 plus I4. So that is 85 plus 3. It is 88 amperes. Okay. Now this is equals to 200 into 15 minus IM is 97.5 square into 0.05 plus 200 into 2.5 plus IAG is 88 square into 0.05 plus 200 into 3. So this is equals to, so we have to do the calculations. If you have calculated, tell the answer, else it is fine.
One 637.3.
Yes. One six. Yes, how much? 16. I don't think so. It is 1037.5. Has anybody calculated total losses?
$1037.48.
Yeah. Okay. So total stray losses is 1037.5. I will take 0.48 is nothing but 0.5 watts. Others are getting the same.
Yes,
Yes,
sir.
sir.
Yeah. Stray loss in each machine. WS is equals to WST by 2. So it is 500 18.7 74 or 75 watts. Okay.
7.5.
It is 518.75 watts. Now we'll go for finding the efficiency of motor efficiency. So motor input P in is equals to V into I1 plus I2. Okay, equals to 200 into 100. It is 20 kilowatt. 20,000 watts. Okay, then motor copper losses is equals to armature copper loss plus field copper loss. This is equals to what? IAM square RA plus V into I4. This is equals to I1 plus I2 minus I3 square RA M plus V into I4. Okay, equals to what is IAM? So we have calculated it as 97.5 square into RA 0.05 plus 200 into 2 point, sorry, this is I3, V into I3, 2.5 equals to
970.31.
yes 9
975.31.
975.3. 0.31 watts. Next, total motor losses. Okay. So Wm is equals to motor copper loss plus stray loss. Is it right? Just go back to the calculations and see. Copper loss in generator. So total copper losses. Calculated copper losses. motor armature copper loss plus motor field copper loss plus motor stray loss. So field copper loss and armature copper loss we have already taken combinedly. Okay, so that's it. So motor copper loss plus stray loss. So this is equals to, okay, what are motor copper loss? 975.31 plus what are stray loss in each machine? 518.75. So this is WM, which is equals to
1494.06.
1494.06 watts. So this is W. Yeah. Motor output, P out is equals to P in minus WM, input minus losses. So it is 20,000 minus 1494.06 equals to 18,506. I will take 6 watts. Okay. You get 505.9 something, you'll take 506. Therefore, motor efficiency is equals to P out by P in into 100. So motor efficiency is equals to 18,506 divided by 20,000.
Two point five.
92.53. Efficiency. Okay. So this is motor efficiency. Next is generator efficiency. So we have electrical output of generator. So generator output P out is equals to V into I2. So that is 200 into I2 is 85. Is it? Value of I2 is 85. Is 17,000. Then generator copper loss is equal to armature copper loss plus field copper loss. That is IAG square RAG plus V into I4 equals to, what is IAG? It is I2 plus I4 square into RAG plus V into I4 equals to, yeah, I2 plus I4 is, we have calculated 88 square into 0.05 plus 200 into 3 equals to 987.2 watts. Then total losses, or you can take stray loss. WS is equals to, it is 518.76 75 watts. In this already we have taken equal to both the machines. Generator losses Wg is equals to Ig square Ra plus V into I4 plus Ws. It is same. Instead of writing in words, I am writing in equations. Okay. So this is 987.2 plus 518.75. This is 1505.95. I will take 1506. Watts. Therefore, generator out input Pin is equals to P out plus generator losses 1000 plus 1506. So it is 18506. 18,506 watts. Therefore, generator efficiency is equals to P out by Pn into 100 is equals to 17,000 divided by 18,506 into 100.
91.82.
91.82. 91.86%. So this is generator efficiency. Okay. So it is ensured that both are almost identical machines. One is 92.53, other is 91.86. The efficiencies are very near to each other. Okay. So therefore, I can consider you do one thing. Also find out the efficiency, assuming both efficiencies are equal. Let me take an additional point here. Find efficiency of each machine, assuming equal efficiencies of both machines. It is just an equation to be used. Okay. I will take it here only. For equal efficiencies, okay, efficiency is equals to, it is under root, line current of motor, sorry, line current of generator divided by line current of motor. Okay, generator line current divided by motor line current. That is very easier way to understand instead of remembering the current values, because if current nomenclature changes, then that equation changes. Okay, so is generator line current divided by motor line current. So as per this equation, as per this nomenclature of current, this is I2 divided by I1 plus I2. ಇನ್ನೊಂದು 10 ನಿಮಿಷ ಕ್ಲಾಸ್ ನಡೀತಿದೆ. ಅಮ್ಮ ಕ್ಲಾಸ್ ನಡೀತಿದೆ, 10 ನಿಮಿಷ ಆದ್ಮೇಲೆ ಬನ್ನಿ. So I2 is 85. divided by I1 plus I2 is 100. Okay, so this is equals to 92.2, 92.19. We are writing 92.19%. Okay. So if I assume equal efficiencies, then efficiency of generator will be slightly different from efficiency of or actual efficiency what we have got. Okay. So if uh, I use exactly identical machines, then this formula is fine. But one problem with this formula or this way of calculation is I will not be knowing the losses. No doubt I got efficiency, but what are the stray losses, what are copper losses, what are field copper losses? Those things cannot be known. If I don't know the losses, then temperature rise, estimation of temperature rise at various losses will not be possible. Okay. So therefore, that efficiency equation with equal efficiency consideration is okay to find the efficiency, but it will not give the entire performance information of the machine. Okay? Complete performance evaluation is not obtained using that. So we'll move to next example. The Hopkinson test on two similar shunt machines. The Hopkinson test on two similar shunt machines. Give the following results. Give the following results. Line voltage 150 volts. Line current 50 amps. Motor armature current 230 amps. Field currents 3.2 and 3.2 amps and 3.6 amps. Armature resistance of both machines is equals to 0.04 ohms. Find the efficiency of each machine. Each machine, assuming a brush contact drop, of 1 volts per brush. Assuming a brush contact drop of 1 volts per brush. So these are the input given, okay, for the Hopkinson test calculations. So draw the circuit diagram for Hopkinson's test. First draw the circuit. So let this be I1. This is I2, I3, I4. This is IAM. This is IAG. Okay. So given voltage is 150 volts. Given things are the results line voltage. Okay, so V is equals to 150 volts. Line current I1 is 50 amperes. Motor armature current. So this is IAM. So which is equals to I1 plus I2 minus I3 is equals to 230 amps. Okay. So field currents, we know that lower value for motor, higher value for generator. So 3.2 for motor and 3.6 for generator. RA is 0.04 ohms. Then I have a brush contact drop V per brush. One volts. So how many brushes we will be having? Generally, number of brushes are equal to number of poles, but here number of poles are not mentioned. So minimum number of brushes are 2. Okay, so consider 2 brushes. Consider 2 brushes. Okay. So these are the given things. Then we have to find the efficiency, taking the given things into account. Okay. So here, this example we will solve in the afternoon class. Okay, in the afternoon, I will be taking the lab session. We'll stop it here because it takes some explanation with brush contact loss also, where all to be added and where we cannot add, all those things. So it is almost up, time up.